Hey Global Impact students, this is Mr. Ellinger here. This lesson is on using graphs to relate two quantities. Our learning target for the lesson, we want to be able to represent mathematical relationships using graphs. Some essential understanding for the lesson. Graphs can be used to visually represent the relationship between two variable quantities as they change. Tables and graphs can both show relationships between variables. Some background for the lesson. Functions can be represented in various ways, including verbal descriptions, equations, tables, and graphs. This is called the rule of 4. A graph in the coordinate plane is the most immediately understandable way of showing how one variable changes in respect to another variable. The table is often useful to provide points for a sketched outline of a graph. We will use mathematics to represent real-world situations from daily life. This is called modeling. By graphing functions, students explore the idea of change, including changes in speed, altitude, distance, volume, time, and other variable quantities. We will investigate the relationships between quantities by using graphs. Alright, so you can use graphs to visually represent the relationship between two variable quantities as they change. So the graph here to the right shows the volume of air in a balloon as you blow it up until it pops. What are the variables? Describe how the variables are related at various points on the graph. So the variables are volume and time. The volume of the balloon increases each time you blow into the balloon, and it stays constant each time you pause to breathe. So that's represented here. If we start at the origin, okay, and we go from here to here, you can see that segment of the graph. As time is increasing, so is the volume of the balloon. So right here we would say, okay, they're done breathing into the balloon, this little flat part of the graph. They're taking a breath, and then they blow again into the balloon here. And then they take a breath, and then they blow into the balloon, and then they take a breath, and they blow into the balloon, and then when we get to this point here, the balloon pops. Okay, and you can see what happens at this point. The volume of the balloon goes all the way back down to 0 instantaneously. Okay, so that vertical drop in the graph all the way back down to the x-axis where volume is 0, that indicates that the balloon is popped, right? Which is actually kind of interesting. So, you know, again, this doesn't, a lot of times when we look at these graphs, we think that it's like a picture of what's going on, like, you know, sometimes we'll talk about like the altitude of things or how high things are off the ground, and we see the graph going up to represent the actual physical property that something is going up. Remember, a graph again just shows the relationship between two quantities. So, you know, as time increases, the volume increases. So when we're at this point here, there is a time and volume pair, ordered pair, that goes with that corresponding point on the graph. All right, so a couple other examples here. What are the variables in each graph? Describe how the variables are related at various points on the graph. So here we have board length. And as time increases, we have the length of our board here. So our board, what do you think this would represent? Well, so we have a board length that's constant here, the constant length, and then after a certain amount of time it drops a little bit, okay? And then again, for a constant or for a period of time, the board length is constant, and then it decreases again. And that is, it's pretty much instantaneous, right? So when you see this vertical drop here, that's like an instantaneous change in the length of the board. And again, the length is constant for a while, and then the length drops, and then the length is constant again. So what's going on here in this illustration? Well, a board, meaning like a piece of wood, is what we're talking about here. So somebody's cutting this board, right? So the board is a certain length at this point, and then right here, there's some cutting that takes place with a saw, or, you know, I'm sure it's a power saw because it's an instantaneous change in the length of the board. And so after that first cut, here's the length of the board. And then, you know, carpenter or whatever could be resetting the board, cutting again right here, resetting the board on the saw, cutting again here, and then possibly using the board or whatever, because there's no more cuts. So maybe this is where they actually use the board in the construction that they're doing. In graph B here, we have June cell phone cost. So here on our horizontal axis, we have minutes of calls, so how many total minutes we have, and then here on the vertical axis, we have the cost. So all along this part of the graph here, we call this a constant, okay? The cost is constant. As the minutes of our calls increase, the cost of our cell phone plan is constant. However, at this point here, the cost starts to increase, okay? And it increases at a steady rate from there on. So, what is going on here? Well, if you think about a lot of cell phone plans will say, all right, you get 300 minutes free. So let's say that the cell phone plan you were using, you got 300 free minutes. Well, this corresponding value of minutes on this axis here would be 300. And then after 300 minutes, the cost would go up so many dollars or cents per minute. So that's what's represented in that graph. Okay, so let's take a look at another problem here where we have a situation. We have some data in a table over here. So a band allowed fans to download its new video from its website. The table shows the total number of downloads after 1, 2, 3, and 4 days. Which graph could represent the data shown in the table? So here we have, after day 1, 346 downloads. Day 2, we have 1,011 downloads. Day 3, we have 3,455 downloads. And day 4, we have 10,426 downloads. Now, the first thing we'll notice in our data is, as we go from the number of downloads from day to day, these downloads are not increasing at a constant rate, okay? So that's going to be key to us in some of the analysis that we're going to do here on out. We increase by 700 approximately, then we increase by about 2,500 approximately, and then we go up with a jump of about 7,000 downloads, okay? So which one of these graphs would represent that? Well, in A, we have these points here. They're definitely increasing. So as the number of days increases, the number of downloads is increasing, right? So that's a possibility. Again, here's another representation of that. Okay, as the days increase, the number of downloads increases. D is illustrating the opposite. As the days increase, the number of downloads decreases. So right away we can throw this one out. So, and then another, part B here, we have an upward trend in the data, if you will. So as the number of days increases, the total downloads increases as well. So the question is, which one of these is it? Well, since things are not changing at a constant rate, the total downloads are not increasing at a constant rate, we're going to throw this one out. That's a line. And one of the functions that we're going to study first is what's called a linear function. And a linear function has the property that things are changing at a constant rate. So then we have B or C. Well, if you kind of take a look at this and see here, as we go from point to point, the values are increasing. But if you look at the change in the increase from one point to the next, so from here to here, then from here to here, and then from here to here, the vertical change is actually decreasing, okay? And over here in the graph in B, as we go from point to point, the change from point to point is actually increasing. And that's what's represented in this table, okay? And this may not be exact, but this is just trying to give us an idea of what the data looks like. So the answer here would be B, okay? So as it says here, we need to know the relationship represented by a table, which we just discussed. We need a graph that could represent the relationship. And then we need to compare the pattern of changes in the table to each graph, which is what we did. So in the table, the total number of downloads increases each day. And each increase is noticeably greater than the previous increase. So not only are the number of downloads increasing, but each increase is getting greater from day to day. So the amount of increase is increasing. So the graph should rise from left to right, and each rise should be steeper than the previous rise. So here you see the rise. There's our rise, and there's our rise, and then there's our rise from point to point. So the rise is increasing each day. All right, so here's another example. The table shows the amount of sunscreen left in a can based on the number of times the sunscreen has been used. Which graph could represent the data shown in the table? So here we have a horizontal table, and the data in this row are the number of uses. So 0 uses, 1, 2, and 3 uses. And then it tells us the amount of sunscreen that's left in the can after each use in ounces. So after 0 uses, we have a 5-ounce can. After 1 use, we have 4.8 ounces left in the can. After our second use, we have 4.6 ounces left in the can. And after the third use, we have 4.4 ounces in the can. Okay? So if we take a look at the data, as the number of uses increases by 1, what's happening to the amount of sunscreen in the can? Well, the amount of sunscreen that's left in the can is decreasing. Now, all three of these graphs show that, okay? They all show a decrease in the amount of sunscreen as the number of uses increases. But what we'll notice here in the data is going from value to value, we're going down by 0.2, down by 0.2, down by 0.2. So what we do, we call this a constant change. Okay, and a constant change on a graph is going to be represented by a linear pattern in the data, okay? So part A is the correct answer. C and B, when the amount of sunscreen from use 0 to use 1 is decreasing, and that's fine. But you'll see from use 1 to use 2, the actual change is a steeper, is a greater decrease from this point here to this point here. And then the decrease is actually even greater from this point to this point. So that is not a constant change here, okay? So right away we can eliminate B. Now the question is it going to be A or C? Well, both show the amount of sunscreen decreasing as the number of uses increases, okay? And both are illustrating a linear change here. So which one is correct? Well, if we take a look at graph A, and we kind of take a look at this point here, this is saying that our fourth data point, the amount of sunscreen left in the can is at 0, and that's not the case here, okay? So when we're torn between two graphs, then we have to kind of take a look at each individual data point. Okay, over here, our fourth data point, which is after use 3, is still showing some sunscreen left in the can, right, over here. So this would correspond with 4.4 ounces, and this would correspond with 3. So this one shows the appropriate relationship here in the graph. Okay, so we would have to throw this one out, and we already threw this one out. So the correct answer here would be C. Okay, and another interesting situation here, we have a model rocket rises quickly and then slows to a stop as its fuel burns out. It begins to fall quickly until the parachute opens, after which it falls slowly back to Earth. What sketch of a graph could represent the height of the rocket during its flight? Label each section. Well, here's the graph, okay? And so the graph, the relationship here is time related to height. And the title of the graph is Model Rocket Flight. That's what we're looking at here, okay? So it's always a good idea to have a title on a graph anytime it represents some real data. So here we go at 0, 0 at the origin. This first part of the graph from this point up to this point is showing our rocket rising, okay? And again, this is not showing like a picture of the rocket. It's not, being shot in this trajectory here. This is just showing the relationship between time and height. So this isn't an illustration of the rocket's actual flight, okay? Like if you were looking at it horizontally, this is just a graph of the relationship between time and height. So we start here, and then at this point, the graph tells us that it stops rising. So we have an increase in the data. Time is increasing and height is also increasing. So it stops rising. And then at that point, from here to here, it's falling quickly, okay? And it's free falling. So if you think about what an object looks like, you project it up into the air, and then at a certain point it stops rising, starts falling back to the ground, okay? And that fall is quick, okay? Now what happens at this point here, we're told the parachute opens. So then what a parachute does is a parachute slows the fall, and this part, it's falling slowly, but you'll notice it's a straight line. So we're going to get into this a lot more, but this means that the relationship between time and height is changing at a constant rate. Okay, so the height of that parachute is decreasing, and it's linear, so it's decreasing at a constant rate. So this is what the graph of this situation would look like. Suppose you start to swing yourself on a playground swing. You move back and forth and swing higher in the air. Then you slowly swing to a stop. What sketch of a graph could represent how your height from the ground might change over time? Label each section. So here we have our time, and that's in seconds. And time is almost always 99.9% of the time going to go on the horizontal axis. And then we have our height on the vertical axis, and that's in feet, right? Okay, so at time 0, 0, or at time 0, our height's going to be 0. We haven't swung yet. So then we're going to start to swing, okay? And we're going to swing higher and higher and higher. But what happens when you swing? You think about what it looks like when you swing. If I just draw an illustration, okay? And this isn't going to be fancy, but okay, so here's a point where the swing is fixed. Here's the swing hanging down, and here's you on the swing, and then here is the ground. What happens is you start to swing, you go back and forth, but you start to go higher, 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 and then you slow down, slow down, slow down, slow down, slow down, slow down, until you get back down to the ground. So how do we draw that? Well, as time increases, so we might swing up, and then swing back down to the ground, and then swing up, and then back to the ground, and then up, and then back to the ground, and up, back to the ground, okay? And then even though my graph doesn't continue on, I'm going to keep, so this is where I would start to slow down, lower, 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 until if I did extend this axis out here, I would be back down onto the ground at some point in time, okay? So that the graph could look something like that. And I didn't draw these using straight lines because when you swing, your height is not necessarily changing at a constant rate, okay? So that's one way to draw this. And without getting too technical with things, you could draw it this way too. You could go, all right, we go up, and then we go down, and then we go up, and then down, and we swing up, and we swing back to the ground, and then up, back to the ground. And then we're going to start slowing down, so it's going to look like this, 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 until we're back on the ground, okay? And again, my graph, I didn't have a big enough graph, but if I extended the horizontal axis out, this would be, at that point, I'd be back on the ground, okay? So that's another way to draw that. And both would be correct at this point. We're not really too concerned with the specifics of the graph. We just kind of want to get a general idea of what the graph would look like. So, all right, so we draw graphs to represent the relationship between two quantities. It's a big part of math, a big part of algebra, because we are going to be studying the relationship between two quantities quite often, okay? Have a great day, folks.